Hello, everyone, and welcome back to Black Harbor's Advanced Horror Series. Going to let Justin take over. Justin?
Yep. Howdy. Welcome back, everybody. Part two today. We are getting into, we have attack path analysis highlighted here, but we kind of went over that mostly in the previous section, but we will be going over attack feasibility, risk value determination, and risk treatment decisions in this portion. So attack feasibility, let's get right on into it. So feasibility, right, there's going to be three types that are outlined within ISO 21434. And which one do we use? Attack potential based approach, a CVSS based approach, or attack vector based approach? Well, we use the attack potential based approach. We want to see how likely it is that somebody's going to perform these attacks and what potential they have to cause damage to the road user in some form or another via those impact ratings that we do. So for feasibility, we now want to try and look at kind of how the impact is considered, right, but we want to have the factors of time, expertise, knowledge of equipment or components, the window of opportunity, and equipment kind of factored into how feasible it might be for somebody to actually perform this. As for each attack path, we want to create this feasibility analysis and rating for it. So to kind of determine the attack effort ratings or the feasibility, we want to use kind of those listed things, right? So the elapsed time, we abbreviate to T, the specialist expertise, the knowledge of item or component, window of opportunity, and equipment. So of course, kind of the breakdown here, the time is going to be how long it might take somebody to perform the attack. The expertise is how knowledgeable in general or in this specific kind of field and realm of kind of experience, how experienced does somebody have to be? You know, can they be just a random layman or somebody who knows nothing about it, but at most maybe saw like a forum thing that said, hey, you can do this, and then just goes out and tries it and is able to do it. And then knowledge of item or component, this is going to be how much kind of privileged knowledge do they need? Do they need something that is readily accessible online? Is it something that a like manufacturer should only know? Window of opportunity, this is going to be kind of ease of access and how kind of it's kind of a distance, but how hard it is to kind of have access to the vehicle, how close you have to be to it, and kind of how long you have that access. And then equipment is going to be, of course, what equipment they might need to perform the attack. If it's going to be something as simple as just like an OBDII connector to send messages over the CAN bus, or if it's going to be something like an oscilloscope or very specialized equipment, right? Like bespoke type stuff. So breakdown here, we're going to kind of roll through all these a little bit more in depth. So time, this is going to range anywhere from less than 1 day to more than 6 months. Of course, this is going to kind of come down to looking at the specific attack path and then kind of deciding how long that might take. If it's something like reflashing an ECU and requires all sorts of background knowledge information and building out like an entire like process, right? That might be greater than 6 months to kind of perform something like that. But if it's something simple like trying to spoof a message, probably going to be less than or equal to 1 day. Now for the special expertise. So again, this is going to be the layman, proficient, expert, or multiple experts, right? So a layman is going to be someone who is not knowledgeable on it at all compared to experts or proficient persons with no particular or zero expertise. So just an ordinary person using step-by-step description of an attack that is publicly available. So this like might be something on a forum or on a video on YouTube or something like that, that just anybody might be able to follow. Then a experienced owner is going to be someone who is proficient, and they're going to be perhaps like an ordinary technician who knows who knows simple or popular attacks such as odometer tuning or installation of counterfeit parts. Then an expert is going to be somebody who is a specially experienced technician or engineer, and then multiple experts, of course, would just be more of those same people. So when we determine kind of the type of attack, again, you then want to look at how easy it might be to replicate, especially if it was found and tried to be spread about. If we have somebody trying to put step-by-step instructions on how to do something that requires an oscilloscope, it's going to be a little bit harder than somebody saying like, "Hey, send these 2 CAN messages every 5 seconds." Fairly different there. So that might be something that requires an expert instead of a layman, or vice versa, depending on what's happening. Now, knowledge of the item. This one gets a little confusing sometimes, but pretty much it is public, restricted, sensitive, or critical information. So the public is going to be something that is publicly available to anybody, right? It might be in the user manual. It might be something that is publicly shared, like a top speed or something like that, right? Things like that that are very easily accessible. And then the restricted information is going to be something like source code and internal documentation shared between manufacturer and supplier. Then sensitive information, this is going to be knowledge that is shared between discrete teams within the developer organization, access to which is constrained only to members of the specified teams. So very sensitive stuff, immobilizer related information, for instance. And then critical information is going to be knowledge that is owned by only a few individuals, access to which is very tightly controlled on a strict need-to-know basis and individual undertaking. Secret root signing key, for example. Pretty much anything that is going to decrypt or encrypt information that somebody would normally not be able to do, or read files that they shouldn't have access to. Something like that would be kind of a critical information type of category here. Then window of opportunity here. This is going to be, again, 0 to 3, and we have unlimited access, easy, moderate, and difficult. For unlimited, this is going to be logical or remote access to one or several targets without physical presence. For instance, via wireless or cellular interface, or by exploiting a critical IT backend vulnerability. More or less, from a distance very far away, you can do it pretty much whenever you want, right? For easy, it's going to be physical access to the interior or exterior of a component, but without using any special tools and without opening the housing of any devices. Pretty much an attacker would be able to use like the OBD port or some other kind of just near the vehicle type attacks. And then moderate is going to be disassembly of physical parts to access deep internals, such as trying to get to some flash memory. And then difficult is going to be disassembly of the item on microelectronic level, or electronic level, such as microprobing, cutting, or chemistry, including breaking some sophisticated tamper protection boundaries. Often many targets, greater than 10, have to be used to successfully develop and execute such attacks. For implementation errors, this rating is to be chosen if all possible mitigation methods for implementation errors are used. So pretty much what this is saying, again, is kind of how easily are you able to do this on a vehicle in terms of time to actually perform, and how difficult it might be to kind of get the pieces of it, right? So if you need to flash an ECU, for instance, you might need to pull it from the vehicle, maybe actually connect directly to it, and that might make it a moderate level, right? Or you're able to do it over the OBD port, and it's an easy one. So again, it really depends on how you explain the threat scenario and the attack paths for it. So now we have the equipment. This is going to be standard, specialized, bespoke, or multiple bespoke. So as I'd kind of mentioned in the beginning here, standard is going to be like a laptop, a CAN adapter, a universal diagnostics tester, or any other ordinary tools like screwdrivers, soldering iron, and pliers. Specialized is going to be hardware debugging devices, or an oscilloscope, or a signal generator. Then bespoke is going to be manufacturer restricted tools such as an electron microscope or other specially made tools or software specifically for this attack. Of course, multiple bespoke is just more than one, right? Just a bunch of very specialized tools and software to try and perform one of these attacks. Now, the way this feasibility rating ends up working is once you have some attack out there that you've decided, all right, let's break it down, see how feasible it actually is. You go through the steps. You find out maybe it's a layman with unlimited access is able to do this very quickly, under a week, and then standard equipment can be used, and knowledge of the item is public, right? So just all zeros. You then look over here at the attack feasibility rating. You can see that it's marked as high for any values that are 0 to 9. And then if we wanted to maybe look at a different example, maybe a proficient person, somebody who kind of knows their way around a computer and a car, is able to like look at some stuff a little bit, and the window of opportunity may still be unlimited, so they're able to do it remotely, so it's still at a 3. And then perhaps this is going to be a more difficult attack that might take around. This one is inaccurate. The one over here is what we should be looking at. So equal to or less than a month. So let's say maybe a 4 there, so we're up to 7 now. And the equipment, they need it. They can use a computer, but they need some specialized software that isn't easily accessible, or maybe they have to make their own. So let's call this specialized, which brings us to, what do we say, 7, 11. So we're at 11 now. And then knowledge of the item. Again, perhaps this is going to be somewhat kind of hidden. So this might be a restricted of K1, which brings us up to a medium or a 14. Awesome. So that's kind of how you'd go about actually doing this. Of course, most of the tools, you would kind of just enter all this and it would come up with the values for you. Now into the risk value portion. We want to determine the actual risk. So to get an actual risk value, we want to consider the feasibility and the impact together. So as we mentioned in part 1, right, impact is going to be the impact that a damage scenario and its related threat scenarios have overall. So kind of how impactful it would be on a road user via SFOP, right? So the safety, financial, operational, and privacy. If those have a high impact, something like a severe, then regardless of how feasible it is, it will always have at least a level 2 risk or higher. And then, of course, here's kind of the risk matrix in general, so you can kind of see how impacts that are negligible, regardless of how likely they are to occur, doesn't really matter that much at the end of the day, right? So again, this is kind of how it all maps out. There's not too much to say here. Kind of just got to look at it and go, all right, yep, medium. It's got a 2, serious, medium, 3, right? Kind of, it makes sense. So now when you get to the risk treatment decision, you kind of match those out. And now you have the outcome of the TARA. They're going to have a finite list of factors that add to stakeholder risks. And all aspects of stakeholder risks, so product assets, threats, vulnerabilities, and organization impact, are all factored into treating risks. Risks are also critical to assets that are used to prioritize improvements of design and set a security strategy for the organization. So what this is pretty much saying is we find a risk, we want to try and reduce, avoid, or transfer or accept that risk, right? So let's say we have a spoofing issue with a specific message. Maybe we want to try and add counters to it. Maybe we want to do something like that to try and kind of mitigate and reduce that risk a little bit. Or maybe you just stop sending that message entirely if it's just not needed. Maybe add it to a different message, right? You can avoid it. Sharing or transferring the risk, this is going to be kind of like a insurance company. So you're saying that we know it's an issue, but in case something does happen, we want to just kind of be insured for that. Going semi-top down now, the avoiding the risk, right? So avoiding the risk by removing the risk source and deciding not to start or continue with the activity that gives rise to the risk. So if a feature has a high risk rating, then you just no longer include the feature, you just remove it altogether. Of course, generally speaking, if you want to add a feature, you're wanting to add it for a reason, right? But if it's so bad that you can't find a way to fix it, end of the day, you might just have to completely avoid it and remove it entirely. So reducing the risk, of course, this is going to be kind of mitigating the risk and taking those actions to do that by applying certain controls. Sharing, as I mentioned, going to be kind of like an insurance company. Acceptance is just going to go, the risk is low enough and it's not that likely to happen. We're just going to say we're okay with it, right? And that's fine as long as the company decided together, like, hey, we've looked at it, we've seen what it can do. You've told us this is how likely it is to happen. We're not going to have to do anything about it because our current controls are okay for it already, right? That makes sense too. But of course, most of the times, if you have a kind of high risk, you do want to reduce it, not just accept it. If it's high risk, accepting is probably not the right way to go. So kind of on the reducing portion here, so we want to be mitigating risks through product design, and we want to typically have this fulfilled through the design modification. So we want to make some change to it, not just kind of add stuff on top of it. And security controls recommendations by security architects and larger research bodies, such as NIST, provide suitable standard security controls for embedded and IT systems alike. So they're a good place to start when you want to look at kind of what changes to make and what kind of mitigation strategies you might want to employ. And we also have specific security controls that are associated with specific risk modifier values that reduce the feasibility of security goal compromise. So that's a lot of a lot of stuff there to pretty much say that as you do add controls, you are able to kind of lower that risk and lower that feasibility, right? So if you look at the feasibility ratings for a specific type of attack, instead of trying to fix the feature or some very specific component, perhaps you want to look at kind of what aspect is the most likely to cause that attack to be possible. If it's something like somebody being able to do it completely remotely, maybe remove that aspect of it or find a way of fixing it to where it's no longer remotely accessible in that manner, right? So a lot of ways to try and reduce it without having to completely avoid it, but lots of options out there. But that is it for today. Thank you for listening in and hearing about TAR Part 2. That's pretty much the run through of all the little steps that go into it. I hope you learned something. Thank you.
Hey, thanks, Justin. Great job. And thank you, everyone, for tuning in. Have a good one.